In the previous video, we have seen how to use device-to-device memory copy to support GPU to GPU communication. In this video, we're going to see another method that is called peer-to-peer memory access. We need to introduce a few extra APIs. The APIs are named as heap device can access peer and heap device enable peer access. By default, peer-to-peer memory access are not enabled by default, and not all the GPUs support this feature. So we have to call this API heap device can access peer to check if this method is supported by GPUs. If the current GPU do not support this method, we probably need to go back to the regular device-to-device memory copy method. And then, if peer-to-peer memory access is supported, we have to manually enable it. It may reduce the performance if we don't really want to use this feature. But sometimes using this feature on particular cases can improve the performance. So let's see how it works. Let's say if we have a 2 GPU system, and each GPU has a 4 GB of memory. Then we want to access the data that is stored on GPU 2 from GPU 1's kernel. How we can do that? So we first need to enable peer access, if it supports peer access. For GPU 1, it needs to create a new virtual address space that maps to the GPU 2's address space. Here, this is just an example that we can use 4 GB to 8 GB to map the GPU 2's address. Now, as you can see, the page table is getting larger, and we will have more chance to have TLB miss, and page table miss, and page faults. Since we have a larger address space, we'll have more chance to have a TLB miss and page faults, which will reduce performance. So you should be careful before enabling peer access because sometimes it can reduce performance. Then suppose GPU 1 wants to load the data. The load request will be sent from the GPU 1 to GPU 2 to load the data, and the data needs to travel back from GPU 2 to the GPU 1 so that the GPU 1 can use that part of data. The communication generally happens between the L1 cache and the L2 cache, so the communication granularity is a cache line. It's either 64-byte or 128-byte, depending on the GPUs that we use. So as you can see, the communication granularity is low, and the latency between GPUs can be very high. So if you're only accessing one piece of data, that can be fine. Or if you can probably pipeline the memory access, that can also improve the performance. But if you have a complex memory access pattern, the performance can be hard to predict. Let's see an example how we can use it. Let's consider a remote vector add. In this example, we allocate the data on one GPU and perform the vector add on another GPU. Here it is a vector add kernel. It's nothing special. It's written as if we are using a single GPU. The special thing happens in the main program. In the main program, we set the memory GPU to 1 and the calculation GPU to 2. So the data is stored on GPU 1 while the calculation that happens on GPU 2. The first thing we need to do is to call this heap device can access peer to check if the GPU supports this feature. If it doesn't support this feature, we cannot perform this experiment, so we simply exit. If it supports, we need to set the device because we want to control the calculation GPU to support this feature. Now we call this API heap device enable peer access to allow GPU 2 to support this feature. Then we allocate a pointer. Remember, we need to set a device to the memory GPU so that this heap malloc can be allocated to GPU 1. Then we copy the data from the host to device so that the GPUs have access to the data. Then finally, we set a device to the calculation GPU. We launch a kernel so that the kernel is launched on the calculation GPU. We synchronize the device to make sure the kernel completes. As you can see here, we didn't do anything special. We're just allocating the data on one GPU and launch the kernel on another GPU. And if this GPU supports peer-to-peer memory access, this calculation can be performed without any problem. You may suffer from some performance issue, but if you can properly pipeline the memory access, sometimes it can be faster. So finally, we set the device back to the memory GPU, then we copy the data back from the device to the host. As a summary, peer-to-peer communication is a very powerful tool that the kernels can remain unchanged. And in the host, you have to check if peer-to-peer communication is supported, and you have to explicitly enable it. Once you enable it, you don't need to care where the data is, you can just directly access it as if the data is local. and you don't need to explicitly call the memory copy APIs to move the data, so it can reduce programmer effort. In terms of performance, it's a little bit hard to predict. Sometimes it can improve performance, and sometimes it can make performance super bad. So my recommendation is to only use it when you can understand it. It's always worth to profile the execution before you deploy your code to know what the performance will be if it runs on a certain level. In these two videos, we basically introduced two methods that allows manual data communication. However, some particular type of data communication, like aggregating the data and calculating average, is very common. And we can see MPI supports this type of method using reduce or scatter or broadcast the primitives. So can we directly control the GPUs to perform broadcast, reduce, and scatter operations? And yes, so in the next video, we're going to introduce a ROCm library that is called RCCL to perform these MPI style primitives.